Good morning, everyone. Thank you for being here again. Thank you, Yuan, for joining us online. And I'm happy to introduce you as our first speaker today from all the way from China is Zhang, who will talk to us about mean field theories for superradiance, frequency measurement, and spin squeezing. The floor is all yours.
Yeah. So
okay.
Yeah.
I now start.
Yes, you can start, please. And
okay.
And people, I would like to ask you for the microphone if you want to ask questions, because we have a remote session. Okay, please, Yuan, start.
Yeah, and thank you very much for the kind of introduction. It's my pleasure to give a lecture in this autumn school. Today I would like to talk about the cumulative mean field series for superradiance, frequency measurement, and speed squeezing. I'm Yuan Zhang from Zhengzhou University of China, and this lecture will cover the following 4 parts. And first of all, I would like to give a shorter introduction on the background, and then I will explain the cumulative mean field approach. And in the third part, I will show 3 examples on the superradiance laser, frequency measurement, and the speed squeezing. In the end, I would conclude and indicate the possible direction in the future. And in 1954, and Robert H. Dick proposed the concept of the superradiance, which referred to the cooperative spontaneous emission of the atomic symbol. And later on, in 1980s, there were extensive theoretical and experimental study on this phenomenon. And at that time, people thought of the superradiance as a transit phenomenon, and people use the laser pulse to excite the atom symbol and observe the radiation pulse thereafter. However, in 2009, and Professor Margie Holland from University of Colorado and suggests that the collective decay can be compensated by an external pumping mechanism. And in this case, we would get a steady state superradiance. And for the system with the optic lattice clocks, and such radiation could have a light waves down to 1 millihertz, and such narrow radiation has high application potential in the quantum metrology. And since then, there were extensive experiment study in this phenomenon, and particular the James K. Thompson group from the same university. And for example, in 2020, and they verify the steady state superradiance by using the Raman transition of rubidium-87 atoms. And then in 2016, and the same group demonstrates the superradiance pulses from optic clock transition of strontium-87 atoms, and also the superradiance from the strontium-88 atoms in the crossover regime. And in this case, not only the superradiance is important, the stimulated emission might also affect the system. And in 2018, and the same group demonstrated the active frequency measurement with the superradiance pulses. And this is a new scheme for the frequency measurement. However, normally people measure the frequency with a passive scheme, and depending on the quantum state we use, and we have different measurement uncertainty. And for example, if we prepare the atom to the speed coherent state, and the measurement uncertainty will scale inversely with the square root of number of atoms. This is known as the standard quantum limit. However, if we entangle the atoms and prepare them to the so-called the spin squeeze state, in this case, the measurement uncertainty will scale inversely with number of atoms. This is known as the Heisenberg limit. There are many ways to generate speed state. For example, the state transfer from the light to atoms, the collision interaction in both incident and condensation, the 1 or 2 twist exit twisting Hamiltonian, or quantum non-denomination measurement. And here we are particularly interested to the last approach. And normally we could achieve this measurement with the system in the weak and strong coupling regime. And here we are interested in under the case with the strong coupling regime was first realized by the James group in 2011. And here they use the 3 levels of the rubidium atoms, and the transition of the 2 upper levels couple strongly with the cavity and leading to the Rabi splitting. And by detecting the Rabi splitting with heterodite detection, and they could refer the population on the middle level and carry out the quantum non-denomination measurement. And if we summarize all these experiments, we found that most of them involve the many atoms in order to enhance the coupling with light, and also they consider the atoms with multiple levels in order to gain high control of the internal states. And also some of the experiments start exploring the quantum measurement effects in order to prepare the atom to the exalted quantum states. And to understand this experiment and propose new scheme, and we have to establish a theoretical model to simulate them. However, for the system with many atoms, the Hilbert space increase exponentially. As a result, we cannot rely on the standard density matrix technique. There are, at this moment, there are few approaches which allow us to attack this problem. For example, the density matrix technique in Dicke state space, or with the collect numbers, or the Monte Carlo wave function in the Dicke state space. And with this approach, we could simulate a system with up to hundreds of atoms. But this approach are restricted to the case with 2-level atoms, and often assume all the atoms are identical, and does not allow us to account the interaction between the atoms. And besides this approach, there is also approximate approach. And for example, the Cumulant mean-field approach. And in this case, we could account for the multiple levels and could deal with the system with identical or with different atoms. We could also account for the multiple interaction between the atoms, depending on the situation we considered. And we could also simulate a system with billions or tens of atoms. And in the following, I would like to shortly explain the quantum mean-field approach. And normally we start from the quantum mass equation for opaque quantum system. And in the mean-field approach, we are interested in the mean value of the operators instead of density matrix. And we can derive the equation for these mean values. However, due to the interaction and the collective process, and the mean value of one operator depends on the mean value of 2 operators, which further depends on the mean value of 3 operators. And this would create a hierarchy of equations. And normally we could invoke the Cumulant expansion approximation to truncate the hierarchy and obtain a closed set of the equation. For example, if we assume the 3rd order Cumulant is vanished, and we obtain a relationship between the mean value of 3 operator with the mean value of 1 and 2 operators. And in this case, we found that the number of the equations is proportional to the force power of number of the levels and the square of the number of atoms, and comparable to the exponential increase in the density matrix approach. And such approach allow us to simulate many systems with many atoms. And furthermore, if we assume that all the atoms are identical, we will find that many mean values are the same. And by removing this redundancy, and the number of independent equation depends only on the number of the levels. And in this case, the number of atoms appear only as a parameter in our equations. And thus, we could simulate as many atoms as we like. By following this procedure, and we could apply the mean field approach to any problem. However, quite often we may made a mistake during the equation derivation or the numerical simulation. Unfortunately, in 2022, and Professor Hamid Hish from Innsbruck University, Australia, have developed a package to derive and solve the mean field equation automatically. If you are interested in this package, and you can look at this paper or the web page of the package. And in this case, and we could avoid any mistakes in the equation derivation and the numerical simulation, and focus on the theoretical model and the physics themselves. And in the following, I would like to show you 3 examples to demonstrate the power of this package. And the first example concerns the superradiance laser, and such phenomenon can be captured by the following quantum mass equation. Here, the commutation relation describes the coherent dynamics, and we model the cavity mode as a quantum harmonic oscillator and consider its coupling and its exchange with atoms. Besides, we also account for the system dissipation, for example, the photon loss and the decay, dephasing, and the pumping of atoms. And here, the pumping is just the inverse of the decay, and describe phenomenologically the pumping mechanism as proposed by Professor Mary J. Holland. And to solve this mass equation, we could follow the following codes. And here I will not go into the details of this code, but only highlight the main steps. For example, and in the first step, we will import the necessary package, and then we could define the Hilbert space for the cavity, for the atom, and the product space for the system. And then in this space, we could define the photon annihilation operator, the transition and the projection operator for the atoms. Besides, for the model, we also need some complex numbers. With this, we could then set up the system Hamiltonian and specify the jump operator and the rates in order to specify the lambda term for the dissipation. With all this, in the next step, we could call on the function, the mean field, to derive the equation for the expectation value of some operators. And for example, here I show you the equation for the mean photon number and the population on the upper levels. And by analyzing this equation, we found that they depend on the correlation of the cavity mode with the atoms. So in the next step, we would like to derive the equation for these correlations, and this is done by this function here. And for the superradiance laser and particularly the third order cumulate approximation we use, we found that the mean value of the photon creation and annihilation operator and the correlation coherence of atoms are 0. Therefore, we could also define the function to remove these terms in the equations. At this moment, we have not assumed that the atoms are identical, so it can deal with the system with different atoms. If we assume the atom identical, we could simplify this equation dramatically. And in this case, the superradiance laser is captured by a closed set of 4 equations. And by comparing this equation with the one I showed you before, we found that we replace this sum here with one term multiplied with number of atoms. And also here for the in the equation for the photon and the atom correlation, and we replace the sum here with the correlation of the first and the second atom multiplied with n-1. So that means in this case we only need to solve a very limited number of the equations. And okay, with this equation, in the next step, we would like to set up the initial value for the mean field and set up the system parameters, and then define the ordinary differential equation with the initial value and the system parameter. And in the end, we solved it with the longer-quota method or other numeric method. With all those code, in the end, we could extract the property of interest, plot them as a figure. And here, I show you the dynamics mean photon number and the population of the upper level. Okay, if you are interested in the spectra, we could also calculate it with this expression. It depends on the Fourier transformation of the two-time correlation function. And the equation for this two-time correlation function can be derived from the quantum regret theory. And this is done by following code. And here we show the equation for those correlations. And normally we are interested in the spectra and the statistics, and therefore we specify the initial values for this quantity here with the statistic property. With all this, in the end, we could obtain the spectra as shown here. And with those codes, and we could easily recover the results present in this article. However, at the time when we write this article, there is no quantum combinator package. Therefore, it takes us a lot of time to derive the equations and make sure that the simulation are correct. And here, first of all, we show you the simulation for the system with strontium-87 atoms. These two graphs shows you the mean photon number as a function of the pumping rate and the number of atoms, and also the spectral light weights. We found that for the larger pumping rate and the larger number of atoms, the photon number can be larger than 1. And the spectral light weights can be smaller than millihertz. So these results are consistent with the prediction from Professor Mary Holland. And here we found that in this case, the minimum light weight achieved is bounded by the percent enhanced decay rate. Then we could also simulate the system with strontium-88 atoms. And in this case, the coupling with the light is much stronger, and therefore the number of photons is huge, and the spectral light weight is not limited by the percent enhanced decay rate. And for the system with a larger number of atoms and also larger pumping, and the spectra can be further narrowed, can become further narrowed. This further narrowing is due to the involvement of the stimulate emission process in this case. Okay, here is a first example. Does anyone have questions in this part?
Do you hear me?
Yes, I can hear you. Yeah.
My question is, why the minimum line with in these plots proportional to a parcel rate? So it's independent of n, right?
Yeah, and yeah, actually, in this paper here, we also develop a method to convert the mean field to the Dicke-state quantum numbers. And if you, unfortunately here, I do not show the graph, but basically the information is that if you pump the system very strongly, and you will prepare the ensemble to the subradial states. And those subradial states have the reduced coupling with the cavity mode, and the lifetime of this subradial states is given by the percent enhanced decay rate.
Thank you.
Thank you.
Any other questions? Okay, so please proceed.
Okay. Now I proceed with a second example and the frequency measurement. And we are motivated by the experiment in 2018. In order to explain what we did in the following, I would like to explain more the details of this experiment. And in the experiment, they use a magnetic field to split the ground and excited state of the optical transition. And by choosing the cavity mode with proper polarization, and they could couple the cavity mode only with the vertical transition. And in the experiment, they use a laser pulse to excite the cavity, and the field formed inside the cavity drive the atoms. And after pulse, the excited atoms will release the energies through the superradiate process, and they mix the superradiate signal with a local oscillator and detect the mixed signal with a photon detector. And in the most of study on the superradiance, and people focus on the process and the process leading to the superradiance, and does not care so much on the measurement. And here we found that the way how we describe the hydrogen detection is also important. And according to the quantum measurement theory, and in the presence of the measurement, and the system dynamics should be described by the stochastic mass equation. And this equation, this part is the one in the absence of the measurement. This is the one due to the measurement back action. And for the hydrogen detection, and this measurement back action has the following form. It depends on the photon annihilation and accretion operator, as well as their expectation values. They also this back action also depends on the efficiency of the photon detector. And in this expression, the DW is a random number, which follow a Gaussian distribution with zero mean, and the variation given by the time step of evolution. And according to this theory, the photon current as measured here is proportional to the real part of the field amplitude, but is dominated by this random number, which actually describes the photon short noise and short time. And due to the limited time, I will not show you the full expression for the stochastic mass equation and the code, but if you are interested, I could send you the slides I have prepared. And in the appendix, I show you the details of the equation and the codes. Okay, by solving this equation, but here I want to emphasize that the quantum complement package can only deal with the system in the absence of the measurement. In order to study the phenomenon as here, and we have modified the code in order to account for the influence of the measurement back action. This is the code that we have modified here. And with this code, now we could reproduce the result shown present in this article. And first of all, we distribute the atom ensemble to 10 sub-ensemble, and calculate the photon number and the population difference of the atom in the different sub-ensemble. And here we see that during the driving, and the atom in the different sub-ensemble has the population of these atoms oscillate with time, but with different periodicity. After the laser pulse, and the atoms in the different sub-ensemble decay with a different decay rate. And following this decay, and we opt this very complex superradiate beat signal. And we could also calculate the photon current, and then carry out the Fourier transformation and opt the normal spectra. And in this spectrum, we obtain the 8 peaks, which are associated with the 9 transition of the atoms. And here, the innerst 2 transitions are not visible because they couple very weakly with the cavity. And here, I want to emphasize that the numerical results and shown here agree perfectly with the observation in the experiment. And this justifies the stochastic mass equation we have and the numerical code we have developed. And furthermore, we distribute the atom to 2 sub-ensembles. And in this case, we get a rather simple superradiance signal. And the power spectrum shows only 2 peaks. And we could also analyze the uncertainty of this, the frequency of these peaks, and analyze the uncertainty as a function of the measurement time. And here, these results show here agree qualitatively with the results as measured in the experiment. Besides this, we also simulate the system with longer superradiance pulse, and we found that the frequency uncertainty can be reduced by 1 order of magnitude. And this indicates that there is plenty of room to optimize in this scheme of the frequency measurement. Okay, about this part, does anyone have question?
If anybody have questions? Okay, then maybe I will ask a short question. Can you probably show us the equations for the stochastic master equation? I would say yes. Here, so here you have some. So this is the expression for measuring back action, and here you provide also some averaged values of operators A and A dagger. So how you take it or estimate, or can you tell us a few words about? Is it from equations without measurement back action, or this is from previous step? Because as well as I understand, this term corresponds to quantum Wiener process. Yes, kind of.
Yes, because in the heterogeneity detection and the quantity measured is the field amplitude. So that is the expectation value of the A and the A dagger, and the quantum measurement back action here is proportional to the noise of the photon with respect to the mean value. So actually, if you are interested in the derivation of this formula, and you can look at this book here. Yeah.
Thank you.
Yeah.
Also questions? No. Okay.
Okay, if there are no question, I will proceed and then illustrate the third example and the conditional speed squeezing. And our study is motivated by this experiment, and as explained before, and here they rely on the heterodyne detection and to realize the quantum non-denomination measurement. And in our study, we suggest that the quantum non-denomination measurement can be also realized with homodynamic detection. And in our proposal, and we use one probe field and split it into 2, and one transit through the cavity, and then the transmitted light combine with the probe field, and then detected by the homodynamic detection. And since the homodynamic detection is also proportional to the field inside the cavity, therefore we have first of all studied the field amplitude as a function of the probe frequency. And here we see that when the probe frequency is running with 2 dry states in the system, and we get some random feature. And then in the next step, we assume that the probe frequency is related with the upper dry states. and then study the field amplitude as a function of the population difference between these two levels. And in this case, we found that the real part of the field amplitude shows the maximum slope for the population difference around 0. So this is a condition we would expect the optimal speed squeezing. So in the following simulation, we will assume such condition. And in our study, first of all, we study the ideal case without the atom decay and defacing. In this case, in practice, we first prepare the atom to the speed coherent state with a collective speed vector pointing along the y direction. And then we probe the atoms with home detection. And we found that the vector component along the direction, the uncertainty of this component is reduced. But at the same time, the collective spin vector also rotate. And we also found that this rotation depends on the probe frequency. So if the probe frequency is resonant with the transition, with this bare atom transition here, and there is no rotation. However, if it is resonant, if it's not resonant, it will show the oscillation. And this rotation of the vector also leads to the oscillation of the uncertainty for the vector component in the equator plane. In any case, the uncertainty along the z direction actually reduces with time, indicating the spin squeezing. In order to understand the origin of this oscillation, and we have calculated the frequency of this oscillation as a function of a probe frequency, and we found the maximum value when the probe is resonant with dry state. And also we found that for given probe frequency and the oscillation frequency increase quadratically with the probe strings. So these two results indicate that the oscillation as observed here can be attributed to the AC stack shift effect. So here is a very simple energy diagram to illustrate this process. So we have the strong coupled atom and photon, which lead to the two dry states. And if we probe this dry state with a probe laser, and the detuning of the probe laser to those dry states would lead to the AC stack shift. And we could attribute all this shift together to the shift of the lower level. And this shift is proportional to the square of the probe strings, and depends also on the detuning of the probe to the dry state. So such a simple expression, and it's play quite well, and the results we observe here. And with this understanding, in the next step, we analyze the influence of the atom dissipation process. And in general, we found that in the presence of this dissipation, the collective speed vector actually shrink. So the length is reduced, and the uncertainty along the z direction is also became a little bit larger. And this effect is directly illustrated in this graph. Here we show the spin squeezing parameter for the z component and the function of time for the different atom decay rate. For the smaller decay rate, the squeezing parameter reduces with time, but it would will rise for very long time. With the increased atom decay, and the rising of the squeezing became more severe. And we found a similar effect for the atom dissipation, but in this case, the value we considered is orders of magnitude smaller than the atom decay rate. And therefore, we conclude that the atom defacing affects the speed squeezing much stronger. Therefore, in the experiment, it is very important to eliminate the atom defacing as much as possible. Okay, in order to migrate the band effect of the atom dissipation, we could simply increase the number of atoms and enhance the coupling with light. And in this case, we simply increase the length of the block vector, and indeed, as shown in this graph, with the increased number of atoms, the rising of the squeezing parameter and the longer time is suppressed. And in the end, we could summarize the calculation we done so far, and here we show the ratio of the squeezing parameter with the number of atoms as a function of number of atoms, and such ratio is proportional to the variation of the angle of the vertical component and the transversal component. And this angle can be actually measured in the experiment. And we found that if we prepare the atom to the coherent spin states, and the minimum, the optimum ratio where scale inversion with the number of atoms, this is a standard quantum limit. However, if we consider the ideal case without the atom decay and despacing, and this ratio will scale inversion with the square of the number of atoms and indicating the Heisenberg limit. If we consider the real system in the presence of the dissipation, and the scaling is in between, right? And here we want to emphasize that the results we obtain here resemble very much and the results in this experiment. Although in this experiment they use the hydrogen detection to realize a quantum non-denomination measurement. Okay, in the end, I want to summarize this lecture. I show you that many model experiments use many atoms with multiple levels, and also start exploring the quantum measurement effects. And the Cumulant mean-field approach can circumvent the problem of exponential increase Hilbert space and allow us to simulate this experiment and give further insights. And the quantum Cumulant package can derive and solve the mean-field equation automatically and allow us to focus on the physics. And the quantum mean-field approach can be successful applied to study the many effects, for example, the superradiance frequency measurement and the condition speed squeezing. And to study the later two effects, we have modified the quantum Cumulant package and to solve the stochastic mass equation. And in the future, there are many ways to follow. For example, we could try to optimize the quantum Cumulant package and to allow the fast derivation of the mean-field equation and the fast numerical simulation. We could also extend this package. And for example, we could try to calculate the second-order autocorrelation function, which allow us to analyze the statistic of the photons. We could also try to combine this package with the quantum jump approach or the non-equilibrium grid function method, and to develop the new methodology. Despite of this possible endeavor, in the theory, we could also apply the existing package to study other effects. For example, the superradiance Raman scattering, the Ramsey spectroscope with delayed superradiance and the deterministic speed squeezing, and the speed squeezing transfer from nuclear to optical transition, and the retrodictive speed squeezing with the partial quantum states, and many more. And with this, I would like to summarize my collaborator, particularly the Klaus Mühlmann from Niels Bohr Institute, Denmark, and also my colleague and the students in Zhengzhou University. Of course, I also want to acknowledge the financial support from the funding in China and in Denmark. In the end, I would like to thank for your attention.
Okay, so can you hear us?
Yes, I can hear you very clearly.
Okay, so do you have any extra questions? Maybe.
If you go one slide back, could you explain us just briefly what you mean by superradiant Raman scattering?
And superradiant Raman scattering, this effect can be understood with this experiment here. In the very earlier slides. And here, in this experiment, and James group and utilize the superradius Raman scattering to mimic the steady state superradius, and the superradius Raman scattering means that here for the Raman process, normally it involves the driving field, right, and also the emission channel. And here for the emission channel, you could couple with the cavity. So when you couple with the cavity, there will be collective coupling between the atom and the light. So in this case, the Raman process actually is a collective effect. It depends on the number of atoms, and in some cases it depends on the quadratic or the square of the number of atoms. And this is clear collective effect. Yeah.
Any extra questions? Okay, then maybe I will ask one more question. It concerns the conditional spin squeezing. Can you probably show us? Could you probably show us the respective slides? It's I think, yeah. So as well as I understood correctly, for this theory of this method, you also apply the quantum cumulant expansion with back action terms, yes or not?
Yes.
Okay, and you use the second order cumulant expansion here, or?
Sorry, I do not hear clearly.
So
can you repeat your question? Yeah.
You perform cumulant expansion to the second order, so you keep the second order cumulants between the variables of different atoms.
Yes.
Okay, thank you very much.
Yeah, if you are interested in the detail, you can look at this paper here in the archive.
Okay.
Yeah.
And the last question: when we can expect the release of updated cumulant package with quantum back action terms and stuff like this?
So I will try. I'm trying to contact with the professor Heinrich and try to discuss with him how to integrate this with the quantum comment package. Even though I could modify the code by myself, but there are other details, and so I need to work together with them. And at this moment, I don't know, and that time I could provide such a package. But I will try my best.
Okay, thank you. If nobody have questions, so I think we can thank Yuan and.
Yeah, thank you for your invitation, and thanks for the audience. Yeah.